Hello everyone, are you able to hear me? Hi Sandeep Mane. Hi Anandita, hi Joshi, hi Richard, hello Sarvna, hello Vidya. Alright, is my voice clear to everyone? Great, great. So even if my voice is clear to few people, I'll be okay. Uh, Alright, good, good. And alright, so till last session, we discussed something about Zookeeper. Zookeeper being a very basic component in the whole ecosystem, specifically for making very small data available to the whole cluster and ensuring the thread safety and heavy synchronization. So Zookeeper is a very important tool. So do you have any questions related to our previous session? All right. There is a question from okay. So there's a question from Savna. Do you have any? If you have any questions, please feel free to ask. Let me turn off my phone. All right, all right. Hi Lloyd. Do you have any questions for me? Okay. So that's Anandita's question. These two are from Sarvna. All right. All right. Okay. So I will go over these questions very quickly. All right. So an identity reducer is basically a reducer which does nothing, which does nothing. Whatever key values are given to an identity reducer are basically given to the output. All right. This is sometimes useful. So people, instead of creating their own reducer, they just use the identity reducer. Okay. All right. This is sometimes necessary for, say, Hive and other languages to basically have all the input coming to a reducer, giving it into the output. Okay. And in such case, what's the point of having a reducer at all? Because the reducer gets all the values in a sorted fashion, and therefore identity reducer will give the output in an ordered manner. Okay, so the ordered by the key. All right. Next question is in pig subjective question. Write map reduce for joining users and tweets table. I tried joining in MapReduce, but reducer values is not in order. For some keys, the joined values okay, comes user table and then followed by tweets table value, and for some keys, the tweets, okay, okay. So I'll have to have a look at your code. So please share your code. And for this particular question, it will be great if you share your code on GitHub. Okay. So I think you had already created a GitHub repository. So you can share, you just add your code there and share it with me. Okay. I'll have a look at it. All right. Okay. Let me have a look. All right. All right. Savna is saying that he has done it in the assignment. So just can you drop me an email because I will miss it in the morning. All right. Now, related to second questions from Anandita. So, can you explain the REST client? All right. REST client is basically a way to call HBase from the using the URL. Okay. So, if you are running your HBase, you can run a HBase REST client as we had provided during the session, and you will be able to query the data from HBase using the HTTP web request. Okay, this is a very reliable way of providing the service to all your customers, because in this your customers cannot say that they don't have access to it, they don't have a client to it. A web client is basically, the REST client is basically, could be anything. It could be a wget, could be curl, could be a Java program, could be Perl, Python, whatever. And the input and output is not in some proprietary format. It's a plain, a simple string. Okay, so have a look at the URLs which we had provided during the session. That should give you a complete idea on how to call an HBase REST client. Also, to access REST, to access HBase via REST, you need to have access to the you need to have access to the sorry, you need to run an HBase REST server. Okay, that too we have provided during the session. And coprocessor, I'll just quickly explain what's a coprocessor. Coprocessors are like triggers. What does it mean? Let's say you want to provide some sort of restriction on a table. Now you should have a complete control of all the incoming requests on that table. So you could create a kind of a trigger or kind of a filter in, so that you can basically examine the requests which are coming to HBase before they actually do something. So you can create coprocessors for those things. So coprocessors are either pre or post. Okay, when you are saying pre-get or post-get, meaning before the request reaches the database, all the pre-functions are called. After the request has reached the server and server has performed and the request is going to the user, at that time all the post methods are used. So for example, pre-get method will be launched when the user sends a request to the server. Post-get method will be used after the server has processed the request and giving the output to the user. All right. So Lloyd's question is, does Thrift has a REST API? I don't think so. I doubt, but I need to have a look at it. That's a good question, because thrift is not a stateless connection. Thrift is opposite of the rest. Rest is basically completely stateless, meaning every time you connect to the server, the TCP/IP connection is created every time. In case of thrift, it's like your native TCP/IP connection, okay, and is not completely stateless. All right. Hi, good evening, Lux. All right, let's move on. So these were very good questions. All right. Now, today we are going to discuss Scoop. Scoop, Flume, Uzi, and Mahat. We plan to do these. These are very small. We will just go through one example of each, and that should be sufficient for for the exercises. Okay, this should give you enough clarity on which one does what. All right, great. So let's jump in. All right. So first, let me copy SSH ID. What is the server? Hadoop 17. Hadoop 17 at hadoop1.nobigdata.com. All right. Now let's try to do SSH. Now it will not ask me password. Oh, it's asking me password. All right. All right. Let's try to do the scoop part. Okay. Where is the slides? Yeah. Here. So Ravikant's point is that are we not going to discuss Spark? Yes, we are going to discuss Spark. We can discuss Spark tomorrow. All right. So I want to dedicate the full session to Spark. Okay. Mostly like 2 hours, complete 2 hours to Spark. And that's why I would like to little hurry up with Scoop and Mahat and these small tools, because it is quite quick. It can be done very quickly. All right. Good. All right. So what exactly is Scoop? It's an open source tool to extract data from structured data source into Hadoop for further processing. It can also move data from database to HBase. It can export data back to the data sources as well, and has extension frameworks called connectors. All right, just like JDBC driver. So basically, in very simple words, if you have to copy the data from MySQL, Oracle, or Microsoft SQL into HDFS, Hive, or HBase, you use Scoop. Also, Scoop can copy the data from Hive, HBase, or HDFS back into any of these databases. And since Scoop work with almost every database which supports JDBC, that means using Scoop you can copy the data from everywhere. Now you may ask that what is so big deal about Scoop? Okay, why are we discussing this? Because if we understand correctly, our MapReduce code is nothing but Java code, right? And from our MapReduce code we could we could write our Java program to copy the data from JDBC and push it into HDFS. All right. So 2 points. Why do we need Scoop? First, it's a it's a ready-made tool. You don't have to code. It provides you all the options of providing the JDBC URL, driver, and everything. Second, it utilizes MapReduce to copy a database table into HDFS or vice versa. All right. So whenever it has to copy a table from MySQL to HDFS, it utilizes the parallelism of map. Okay, part of the table get copied to node 1, part of the table get copied through the node 2, and so on. And that is the advantage of using Scoop, and this is really great if we talk about multiple systems. Now you might wonder that what's the point, because there is only one database node from which all these nodes of Hadoop will be pulling the data. Please note that reading the data is easier than writing. Therefore, write can happen on multiple machines while reading can happen from the single machine. Therefore, reading the data from MySQL and writing to Hadoop system is considerably faster. All right? So Scoop is mostly like a mapping or ETL tool. Thank you, Sanjay. All right. So these are the various command line arguments provided by Scoop. We can quickly check. Okay. So you can say Scoop help, and you will get all the options available to you. It can generate code. It can create Hive table. It can evaluate an SQL statement and display the result, and it can export an HDFS directory. So whenever whatever the definition of export and import comes from, assuming that you are standing on HDFS side. So when you're standing on HDFS side, export means taking data from HDFS to outside, meaning you are standing on the Hadoop side. So if you are saying exporting means exporting means taking the data from Hadoop side to SQL. All right. So import is importing the data, import all the tables, meaning you're basically copying everything into HDFS, and list all the databases, list all the tables, and merge. Okay. So we will just go through Scoop. All right. Now, Scoop provides connector. It's a modular component that uses extension framework to enable Scoop imports and exports for a data store. Available connectors may be MySQL, Postgres, SQL, SQL Server, OBD, DB2, and a generic connector. Any database that supports JDBC. Okay. So third party also Nadja and Teradata. You can copy data from all of these sources, and the fact is that JDBC connectors are available for almost every database on the planet. Therefore, Scoop connector is available for almost every database on the planet. But in case you don't have a connector, you don't have a connector available, you can simply extend the extend the extend existing driver using Scoop connector. It's a very simple to do that. All right. Now let's try to create a database. All right. Let's try to create a database and then try to access it. Now the most important thing to remember is that whenever we are copying the data from MySQL to HDFS or Hive or HBase, the communication would happen from your MySQL to any of the node in the Hadoop cluster. That means when you are creating the database, make sure that your database is accessible to all the nodes. This is a very common mistake. By default, every database, MySQL and everything is great with respect to the default permissions are only to access the local database. Okay, generally by default when you install MySQL, the you cannot access MySQL from the remote, and to make that possible you need to give it the permissions. Okay, and this is a very common mistake, and most of the people who work on a single node and they are very happy that their scoop command is working fine on their local machine, but the moment they put it on the real cluster, the command keeps on failing and they don't know what's wrong with it. It works on my machine. Okay, their common excuse is, the reason is that their multiple machines will be talking to MySQL, and therefore it is important to make sure that the cluster can access the MySQL database. So the easiest way is to go to all the machines in the cluster one by one and check if from the command line you are able to connect to MySQL. Okay, right? So I think the MySQL is working already. Let's try to connect. Yeah, it's working. Great. Let's try to create a database. It says database already exists. I'll just drop the database. Drop database scoop ex3. All right. Now let's create it. The database has been created, and let me give the permission to all Hadoop 1, Hadoop 2, Hadoop 3, Hadoop 4, and so on. All right. Let's try to, once we have done it, let's try to go to another server, say Hadoop 2, and we say Hadoop 17. Okay, so we are connecting to Hadoop 2. All right, so now you can see that let's try to say MySQL. Okay, MySQL minus host Hadoop 1 dot no big data dot com minus u is root. Now you see that we are able to successfully connect from here. Okay, we say show databases, and it shows the database. I say scoop ex3 and show tables. There is no table. All right, so from Hadoop 2 we are able to connect to Hadoop 1. Sanjay's question is the data transfer both from and to database and Hive? Yes, is both from and to. All right, you will see that. All right, moving ahead, so we have successfully created a database which can be accessed from anywhere. Let's now go to our Hadoop one. And please note that we will be using multiple servers, multiple consoles at the same time. So don't get confused. If you have any doubt, just let me know. Right now we are creating a table, okay, and adding some values to it. This is the sample data. We are saying select star from widgets. So we have just created we need to first we need to first create we need to first use this newly created scoop ex3, and then all right, what does it say? There is a syntax. All right, let me just copy paste it in notepad, that is easier to do. So create table. Yeah, all right, let's just try to do that. Now let's see if we have successfully created the table or not. Let's this was a mistake. All right, so we have successfully created widgets table. Okay, and all right, all right, so we have successfully created the widgets table, and all right, now we will copy this table to our hdfs folder. All right, so to do that what we are going to do is we are going to execute this command. Let me make it a plain text and make it look cleaner. So here it says that Scoop, import data from this. Is the font clearly visible to you? All right. So scoop import this, and we are saying table called widgets, and here is my login password. All right. Now let's try to go to the command prompt. So here is my command prompt, and note that right now we are on the Hadoop 2. It doesn't matter. Okay. Hadoop 2 because it doesn't matter because we are copying from MySQL to HDFS, and HDFS is same for all the nodes. Okay. So it's saying that the output directory is already existing. Let's try to delete that output directory. We say rmr widgets. All right. Now you can see that it's properly a MapReduce job, which is being executed on the cluster. You can have a look at it. All right. It says that it's running, and also note that the name of the job is widgets.jar. Okay. I'll show you. Yeah. So it's doing its job, and at the end of it, it should be able to create a widgets folder on HDFS. Hadoop fs -ls widgets. Now inside widgets, you will see part m0. Okay, this is your file. Okay, let me try to say cat, and not this way. I'll have to say cat widgets. Okay, so do you see that? So that inside part M, you have these records. So whatever we had created in SQL, we have successfully imported those records onto the HDFS. Now, also notice that when we did import, it created something called widgets.java. Widgets.java is a good way to reuse the code. So widgets.java is a class which you can use in your other Java code to read the data from SQL and execute, because it has all the logic that connects to MySQL and does the job. All right. Okay, now let's say we want to put this data what we have just imported into Hive. And as we have all done earlier, we can create a Hive table and load the data from HDFS, right? But that will be too clumsy. We'll have to again create table and figure out all the data types and all of this. So it'll be too time consuming. For that, Scoop gives you an additional functionality to just create table called create hive table. Now let's just create a hive table. For this, let me just open one more console. I hope that's all right with you. So there is one console dedicated to my MySQL, second dedicated to my scoop commands. Now let's go to the third one and say ssh hadoop 17 at Hadoop maybe 3 dot no big data, or maybe just say Hadoop 2 dot no big data dot com, and let me copy paste the password. Copy and paste. All right. Now we have all these three consoles. Now using the third console, what are we going to do? We are going to use the HDFS commands. All right. So this is for creating our Hive table. Now, so this is our second for scoop. This is for scoop. Okay, echo, scoop, okay, whatever. Now, third one is I'm planning to start Hive here. So first one for SQL, second one for normal command, and third one is for Hive. All right, let it load. All right, now let's have a look at show databases. Okay, and we'll just use default for time being, and we'll say show tables. And under the table, you see widgets. We can say drop table widgets. Good. Now using this command, we can create, all right. So it says that, not sorry, we from here we can create the table. All right. So what it is doing is it's creating an empty table in Hive. All right. I just hope that it has not deleted my data. Well, when we dropped the table from Hive, I'm just hoping that it has not deleted Hadoop fs minus ls. It's there. Good. All right. Data is there. Now we can easily copy the data and check in our database. So right now let's go to Hive and say select star from widgets. So in Hive, there is no data right now. Now let's try to import, but table exists now. The table has been created by Scoop. All right. So we first imported the data from MySQL to HDFS. Now, second thing we did was we created a Hive table with empty data. Now, third thing we are trying to do is simply the way we learned in learning Hive, that load this data in this particular location into the table called widgets. All right, let's try to do that. We'll go to the Hive command and say load data in the paths into this. Now let's have a look at whether it has. So see, it has successfully copied the data. I mean, it has not copied, it just moved the data. Okay, you can check if it exists still. So the data has been removed from normal HDFS place and has been moved to HDFS folder where Hive keeps its warehouse. Okay, now we have been successfully do two things. We have been able to successfully do three things actually. First one we did was we copied the data from SQL to HDFS. Second, what we did was we created a table in Hive directly based on our SQL table. And third thing we did was we loaded the data from HDFS into into our newly created table in Hive, which is not new, which we with this act is not new. We have already done loading of the data from HDFS into Hive. Now you could do all of these three things in a single step. We could simply copy the full table and create it as well in a single shot. Okay, instead of three steps, we could have just done it in a single step. So let's try to say drop table widgets. Okay, and now let's try to do it in a single shot. All right, now here note few more things which we have not noted yet. Okay, first thing you should note here is number of mappers. Typically, typically you see here minus m1. It means you can specify how many number of mappers you want. Okay, so a job could be executed using multiple mappers if we say minus map equals to 10 or 5 or whatever. All right. Now, the added advantage of this is that all the multiple nodes will try to connect to MySQL and read data parallelly from MySQL and write. All right. So that is a very big advantage. And it doesn't have any scoop program does not have any reducer. Therefore, you will notice inside earlier you must have noticed that part minus m00. Had it been part r, that means it is from the reducer. Part m means it is from the mapper directly. Okay. Now it says that the this particular place already is existing. We have to remove this. All right, and then execute the same command again. All right, sounds good to you. All right, in the similar fashion, we could copy the same data into HBase using scoop import and then specifying the SQL URL and say HBase table is this, column family is this, and username is this, and HBase create table is the actual command. Okay. Also, please note that we have two extra things here. One is column family. It says that create copy these columns from from MySQL. So what HBase create command does is it copies these column values into this column family. All right. If you have to copy into multiple column families, you can run the same command again with different columns and different column family. Also, you have to mention, I mean, if there is no column with the name called ID, you will have to mention that what should HBase consider as the row key. Because if you recall, we had talked about every HBase has a row key. So when we are copying data from MySQL to HBase, you will have to mark one of the columns as as the row key, as the column which is going to go by default and which is going to be considered as unique value for the ID. All right. And because of this column only, it will try to parallelize things on HBase. Sounds great? All right, so we have successfully created a table and also you can see you can see that we have been successfully able to do it in a single step. All right, going now let's try to push it to HBase. Okay, let's try to push it to HBase and see what errors do we get. Okay, now in the third window, I will exit from Hive and will start HBase shell. All right, what does it say? It says column not found called widgets. Now, what column do we have in our MySQL? What did we create in this sample data? All right, what did we create? We had something called, let's say, version. All right, and the second command which we were trying to execute is here. So we are saying SQL import this from this database, this table, and into into an HBase table called customer. Let's first try to delete this customer customer table. Okay. Do we have a customer table in HBase? All right, yes, it is there. Let's try to say disable and say customer. Did it work? All right. Here there'll be a command called disable table. Disable table undefined method table for this. Just a second. Disable customer. All right, it is done. Now we can say delete, and how did we drop? All right, it's done now. So there is, if you say list, it will not be there anymore. All right, now let's try to import. Let's try to import this data. So we are saying from table called widgets, we want to copy into HBase. The column family is CF1, and we have username this and password this is for SQL, and we have to create an HBase table for with a column called ID and the, let's say, price. Okay, let's say price, or let's say widget name as well. All right, now let's see what error do we get. Okay, so it is trying to do some things in parallel, and it has launched a MapReduce job as well. Okay, you see customer, we can say scan. Nothing has come yet because MapReduce process is still going. Now see, as soon as map has finished, we have got data in HBase. So we were able to successfully move data, copy data from SQL into HBase. Sounds great. All right. So that's how we copied the data from HBase. Now, if we have to copy data from Hive to MySQL, we could simply say export instead of import. All right. Okay. So here is a question from Sanjay. So his question is, uh, if we have to take multiple column family from single MySQL table, what will we do? We will have to call this command twice. Okay, like for example, say we want to put the other columns, like the remaining columns, like design date, okay, version, and design comments, okay, into another column family called CF2. All right, now the problem would occur that this table is already created and we have not added that column family. We need to create this column family upfront. Okay. All right. So let's try to see what is happening. Nothing much has come yet. Ideally, it should give an error that the table is already existing and you are trying to add one more column families. Let me also see what happens. All right, this is clever. So they have actually created a column family, probably by deleting the old table and creating one more. So you can see that it has created the second column family. Brilliant, brilliant. So the theory did work. As in, if you have to copy into multiple column families, this is how you can do it. Sounds good, Sanjay? Great. Now let's move on. So now let's say we want to copy data from Hive to MySQL. Okay. So let's see if let's first create a Hive table if it is not there, and we are trying to create a table called sales. All right. Let's see if we have already. Now instead of HBase, we will exit from HBase and we will launch Hive. Good. Now we go back to, let's say, select star from sales. All right, we already have this data created, so we don't need to do this step. We already have this sample data. Now let's try to have, so the next step would be to create MySQL table. As of now, our scoop is not able to create a table in MySQL if we are taking data from Hadoop to MySQL. Okay, so it's not able to, you will have to do it manually. All right, there's a quite much chance of creating the making mistake here. So let's say we have sales table here, and all right, let's just create the table here. Okay, so select star from sales. It's not empty, it's empty yet. Now we will launch this. Okay, here is our Hive where we have this sales table. We want to take it to SQL, which is having the empty records. So all we do is we run scoop export, and then we provide the URL of SQL. We provide number of mappers, and then we provide the table which we are importing. Okay, so you can see that the process still is a map reduce. There is a mapper that is running, and all right. Good. Now let's have a look at it. So we have been successfully able to import data using Scoop from Hive. All right. In a similar fashion, we can also import from HBase and also copy the data from HDFS. All right, this is nothing but, if you notice it, it's nothing but copying data from HDFS. It's not really copying the data from Hive. It's basically copying the data from HDFS. It's saying that this is the export directory, and these are the input files, and these are the username and password. Okay, all right. Now, the next tool which we want to discuss is Flume. All right. Now, what exactly is Flume? Flume is a distributed, reliable, and available system for efficiently collecting, aggregating, and moving large data from many different sources to centralized data store. What does it mean? If you have, let's say, a great data center, if you have a great data center in which there are 50, 60 machines parallelly running various kinds of services. Now let's say all of these machines are producing certain amount of data, maybe in the form of logs or maybe in the form of other matrices. Now you want to copy this data continuously into a central HDFS folder. There are two ways to do it. One is you write your program which will keep on reading this file by using tail, by tailing a file. Do you know what is the meaning of tail? Tail minus f basically prints whatever is happening in the system. All right. For example, if you want to see tail minus f var log, okay, and let's say we want to see some spooler. Okay, how can I pick the spooler for today? Um, or let's say on this is Hadoop 1, right? Hadoop 2 and Hadoop 2. Okay, let's just show you this. So on Hadoop 2, let's say there is a file which we created called test.txt. Okay, some process is trying to read the same file. What was that? Text.txt. Okay, here it's waiting on the second terminal. In second terminal, it's waiting for this text. Now on the third one, what you start doing is you start writing to it. Okay, how do you write to a file? You say hello and redirect to text.txt. Okay, now if you go to the first screen, the process will immediately receive this data. So this is called tailing a file. This is very useful in case of this is very useful in case you want to say there is a command called yes. Yes is not there. Okay, so you can see, so whatever data is being generated here is appearing on the other screen. All right. So one way to collect data is monitoring the files on all of your 50 servers and then taking that data manually to HDFS, say by creating a fresh new file in the HDFS folder, or you could use Flume for the same purpose. Now Flume is extremely powerful in the sense that it can read data. So you got the picture, right? So let me repeat. Let's say you are running 50 machines parallelly and you want to gather matrices, or you just want to gather some amount of data being generated on all these machines. One way is you write your program to read this data on every node as and when it changes, and then push it to HDFS by creating a fresh new file or appending to an existing file. Or you could use Flume for exactly same purpose. Flume comes with far more powers and Flume is very useful out of the box. And we seem to ignore Flume pretty much when it comes to do this kind of job. We think that continuously reading log file or continuously reading a file and or continuously reading a data from a service and pushing it to HDFS is a job which needs to be done by only the streaming tools. Okay, but that's not the case. If you do not have much of a transformation happening during the transport of a fast moving data, if you don't have much of a transformation happening while moving this fastly coming data or fastly generating data on all these machines, then you don't need a streaming solution. Your problem can be solved with Apache Flume. Okay, we will show you that quickly. So Lloyd's question is, do we have an equivalent in Windows for tail minus f? You don't, but you can actually monitor a file in Windows. Okay. The C Sharp API for reading the file provides you a way to monitoring the file changes. Okay. Now the Flume is exactly for these kind of purposes. Now Flume has to be installed on all the nodes in the network. All right? And once you've installed all the nodes in the network, you also specify the configuration of Flume. Okay? We will show you that. Every Flume agent does its job. Every Flume agent transports or or does a very rudimentary transformation from one form to another. Okay? And just like any other reader writer problem, it also has the consumer and producer model. As in, let's say it has to upload the file, the data being generated in a file to HDFS. Okay, so it has to read the HDFS file, and then, sorry, it has to read the local file in which the data is being generated, and it has to push it to HDFS. Now, what if the data that is being generated locally is really fast? Okay, every second the data is being generated, while the data while the HDFS is accepting the data at a slow pace. Okay, so to to neutralize this difference of speeds, we it uses something called channel. So as it keeps on reading the data from the reader, it keeps on pushing it to the channel, and from the channel it keeps on pushing it to the sink. So agent has been cleverly designed in this manner. So every agent behaves like a producer consumer in itself. It has got something called source, it has got something called channel, and it has got something called sink. I think best analogy for agent is this wire. Okay, this is a USB wire in which there is, on one side it has source, and this wire is a channel, and the other side is the sink. Okay, although this here channel's role is to basically only transfer the electricity, but in our case this channel works like a pipeline. Okay, let me explain again, because this will come up again when we talk about streaming. Okay, so what happens in these scenarios? So every system which you build in distributed models, you will encounter this kind of situation almost everywhere. Even in even in the product which we built for Amazon, for pushing large amounts of notifications and processing them on multiple machines, we had to have this exact same model of source, sink, and channel. Okay, so it's called, this is producer, this is consumer, and this is the pipe. Okay, so let's say you are reading the data from tail. By tailing a file, by following a file continuously, that is your source. Sync, as in you are trying to save the data in HDFS, and channel is common for them. Channel could be in the memory, channel could be in the disk, channel could be partially in the memory, partially in the disk. Okay, now there are few characteristics which you should understand about this model. It's not anywhere you are building a producer consumer, you will encounter such kind of things. Now, having source and sink solves multiple kind of problems. One is that source and sink and channel are all movable components, as in you can create all permutations of it. Let's say today you are reading from tail, tomorrow you might be reading directly from the Java log, so you can remove this source and add some other source here, or you can just change the configuration to read from Java log. You don't have to change the sync. But tomorrow, let's say you want to write into HBase, you can write into HBase by just changing the sync. So this way you can do a lot of things. Okay, if you had to build such kind of system, either you could have created all combinations of agents. One who picks the data from tail and puts it into HDFS. Second kind of agent picks the data from some other model and puts it into HDFS. And same thing you'll have to do again and again for all kinds of output formats. So this makes it very modular, makes it possible to do all kinds of permutation. So if you have three kinds of sources and two kinds of uh, sinks, you can actually do 3 into 2, which is 6 kinds of transfers. Okay, and this is very interesting design. All right, now what does the channel do? Okay, so source the speed at which source is generating data might be very fast, and sync might be slow, but sync might be able to store lot of amount of data in a single shot. Okay, but it might take a little bit time. So to solve these kind of circumstances, a sync is mandatory. Okay, one is, so this also solves the problem of whether the multi-threading things. Okay, so channel is generally thread safe, and these sinks and source can use multiple threads parallelly automatically. Now the other properties of channel is, in case channel becomes full, source will stop writing to the channel. If channel is empty, sync will wait for channel to produce something, and that's how the synchronization happens. All right. Yes. Sanjay's question is, can there be more than one and different type of syncs? Yes. All right. Now you can have a look at this way. These agents can be concatenated in a sequence. Okay, we can combine these in various kinds of topologies. So it's reading the data from src, putting it into sync is reading the data and then sending it to somewhere else, so other agent, and so on. We could combine these like these. Okay, one, there could be a sync which is writing to multiple destinations, and there could be source which is reading from multiple sources. Okay, so this way you can basically think of all kinds of topologies, and you will realize that this is a very modular tool to gather or transport data from one place to another. Okay, so Flume supports a large variety of sources including tail minus f, syslog, as in Unix all the logs are generally through the syslog process, and log4j, it can read directly from log4j also, allowing your program to store the data, your logs, into HDFS. So for example, I'll again go back to how we debugged the real-time Amazon's website. Our logs from all the web servers at Amazon were being pushed to a central machine continuously. And on this central machine, we had a small application which allowed us to do the grep, to do all kinds of things from the browser itself. And on this central machine, there were another tool which was continuously running on this newly created logs, which was basically predicting that these kind of errors are being dominant. So it was grouping by the the masses which was coming. So for all of these kind of magical tools which help you debug your real-time website or solve your real-time website's problem, you need to gather the logs instantaneously into a central machine. Okay, only then you will be able to predict, okay, there is something seriously wrong with our servers, let's roll back to the previous version. And those kind of things can only be done if you have all the logs from all the machines available immediately for churning. Okay. All right. So Flume nodes can be arranged in arbitrary topologies. Typically, there is a node running on each source machine with tiers of aggregating nodes that the data flowing through on its way to HDFS. Okay. Now we can configure Flume to do two things by either we can do best effort delivery, it doesn't tolerate any node failures, or end-to-end delivery, which guarantees delivery in node failures. All right, let's try to get it done. All right, let's try to copy this data. I think it is available already. Um, Hadoop fs minus ls slash data. Do we have Flume? Yeah, I think we have Flume. Let's copy this Flume's data locally. All right. So we'll say Hadoop fs copy to local, copy to local. L has to be capital, and we say data Flume, and all right. Now let's see if it has copied. I think it has copied. Oh, it did not copy. All right, that folder seems to be empty, I believe. Never mind. Let me try to copy. This is your SSH student at Hadoop 1.nobigdata.com, and we say sgiri, and we have Flume, and this is my config. So we'll say Hadoop fs minus copy from local conf to data Flume. All right. So, and also we will give a permission on this data using here saying minus ch mode 755 minus capital R. All right. That means now we can copy the data here. All right. So inside Flume, inside, okay, so we made a mistake. Instead of copying it outside, we have copied it inside. All right, so we have conf. Now inside this Flume properties, what we will find is this information. So, so the reason I have copied it in the slash data slash Flume, so that it is available to you instantaneously rather than downloading from here. Okay, so I've put it there. All right. Sanjay is saying, can there be? Okay, good. Nothing, no, nothing new. All right. So this is how the configuration of Flume looks like. You have got you have got first of all, this is the name of agent A1. Okay, this is the name of agent. For agent, this is the list of sources. We could say R2 as well. Okay, and we have got sync. Similarly, we could add more sinks into it. Right now there is only one sink called S1, and then we could have channels as well. All right. Further, we could describe what exactly does R1 mean by saying R1 dot type equals to netcat, R1 dot bind is to localhost, R1 is running on port number this one. So what does it mean? When we run this agent, it is going to run netcat, which is reading from this particular, which is read listening at this particular port in the local host. Okay, and then you have sinks. Sync says that whatever we receive, we will be writing to the HDFS. Okay, now let's have a look at where does it take us, and where is our Hadoop file browser, and there we will say we'll change this for our user. What is the name of our user, by the way? Hadoop 17. Hadoop 17, and let's copy the password again and paste it. All right, so here this is Hadoop 17, and looks like everybody's data is here. Good. Now moving ahead. Now here, so what is our home folder? It's called Hadoop 17. All right, let's just change that. Here, let's just put Hadoop 17. We will change it in our folder. Never mind. Okay. All right. Now, next step is to define the channel. We are saying our channel's type is memory, capacity is this much, and transactional capacity is this much. Okay, meaning ability to do number of transactions is something like this. Okay, so next is that we bind the channels. So here earlier we told A1 about its sources, okay, A1 about its sink, and A1 about its channels. Now we are telling A1 the R1 about its channel. So we have to tell the sink about the channel, and we have to tell basically the source and sink also need to know about the channel, because sink has to read from the channel and source has to write to the channel. All right, and next we can simply run it. Now let's have a look at it. So we have got this properties, flume dot properties. Okay, the same thing is described in here. All right, I hope it's clear. Now we run our flume agent, and here there are few things to note. One is we are providing a configuration folder, and second is we are providing a configuration file, and also we are providing a name. Name is A1, and then we are running it with this other information. All right, now so it says flume ang is not installed. All right, then we will try to run it here. Never mind. Hadoop fs minus copy from local, copy to local slash data slash flume to. All right, so we have flume, and under this Okay, now what you notice is that it is listening on this port, this port called 444. Also, we'll have to see, just a second, we'll have to change few more parameters, vim conf and flume properties. And here let's just change this folder because um, as Giri is not valid, it will give an error when we try to write the data. Hadoop 17. Okay, and we will try to write to say flume underscore web data. All right, now we are going to launch it again. So it says that it is ready to do the job. All right, it is ready to do the job. Now on Hadoop 2, we can say Hadoop fs minus ls. Has it created that particular folder? Where is that particular folder? It is not created yet. No worries. Again, we are still on Hadoop 2. From here, we can connect to the running Hadoop 1.nobigdata.com. I think it will not work because it requires the service to be on the, yeah, because it's running on one to this particular port. Okay, we'll have to log into one itself. Okay, because it is bind to 127. If you bind instead of this IP, if you bind to 0.0.0.0, you will be able to connect to this socket from anywhere in the network. All right, so to be on the safer side, it is generally okay to run a local service. Okay, but in reality, if you want your machine to behave properly, then you will have to run it on 0. All right, so here it's listening to whatever you are writing, and here we will keep on checking whether it has written the data or not. Okay, and is it written? Not yet, I think. It has not created a folder. Let's try to connect to this service, localhost, and what was the port? 44444. All right, now it is connected. We say this is Sandeep Giri. All right, it says okay, and let's say it has created the folder or not. What was the name of the folder which we were talking about? So I'm just writing some random data into that. Is it happening or is it giving some error? It is giving error. It says Hadoop 17 permission is denied on this folder. Oh, that is correct because our folder is wrong. We had to remove student. All right, good, good. Now this has got disconnected. Now let's connect again and start sending some data. This is some amount of data. This is some amount of data. All right, let's see again what has happened. All right, looks like this time it is able to write. So it has created a folder called Flume data, and under which we can see. All right, you can see here as well if you refresh. All right, so here is our folder. So it's continuously writing into this file in a format called long writable and bytes writable. You can see that whatever we have typed is coming here. All right, now in the same way you can have a look at another file. All right, some amount of data. You see that? All right. So that's how we could copy the data. Now there is a question. All right. So is everybody clear that we are trying to do what exactly are we trying to do? So we first started our Flume agent, which was waiting for us to write data on a particular port. Then we started writing data continuously, and it kept on creating the files under this particular folder. Okay, as and when we were writing. Okay, so it creates first temporary file and then it writes to it. Also, if there are multiple clients connected, it can make sure that the data goes by creating temporary file, it can make sure that the creation time is intact. All right, there's a question from Sanjay. What is the fault tolerance and recovery mechanism and Flume source sync model? Because all goes to a central store, and if that fails, how is the data synced? All right. So the way the system just failed. We uh, we generally we sometimes lose data in all of this. Okay. Therefore, what people do is they sync data via multiple channels parallelly. Okay, they sync data via multiple channels parallelly, the way we had discussed in this. Okay, so if you are worrying about these multiples, if you're worrying about the fault tolerance in a network, you generally build a network like this. Okay, it does have a configuration that it will maintain. All right, it does have a configuration that which will it'll keep on trying until the destination is found and give up after some time. All right, so now coming to the next question. Next question is, can you explain the parameters which mentioned in the Flume start command? Okay, let me try to explain. Here, here is the command. It says that we are starting Flume ng. It's a next generation of Flume 2.0. We are starting an agent, and this is our config directory, and this is our config file. Okay, and we are saying this particular agent's name is going to be A1. Why is it so? Because generally what we do is we plan our everything and create a single Flume property file. Okay, so that we edit it once and ship it to all the nodes. Just that while launching, we say that okay, we are talking about A1. So A1's property are picked up from here, and the agent is started. Now this is the logger, as in what all kinds of errors does it need to log. Okay, this is generally for debug purposes. All right, now is that what you wanted, Lloyd? You might have said this already, but why it created so many files? All right, let me come back again. Why it created so many files? Here you see, so as and when we are pushing more and more data, it will keep on writing the data. Okay, one way is it keeps on one way could have been that it could have kept lot of data in a single file, right? But that way it would that way the timestamp of various messages will not be very clear. Okay, So to continuously push data into HDFS, it generally makes sense to create more files. Okay, but you can increase this size by fine tuning the configuration parameters in in your output. Okay, in your output, if you increase the transaction capacity to 1000 or something like that, then it will have 1000 bytes of per transaction capacity. All right, not this one, it will be, I think, somewhere here. Okay, you can have a different parameters in this. All right, all right, great. Yes, since it has so many small files, it might increase the load on the name node. But generally, what people do is they they keep on reading the data of Flume every day using some mechanism, and then delete all these files or compress these files every day and convert them into a single archive. All right, that's how it generally happens. All right, so that was about Flume. Now there is something called Oozy. Oozy is a workflow just like, not like BPM. It's not like a workflow as defined in BPM, but it looks similar to that one. All right, here is an interesting question from Lloyd. If we have Windows IIS server, can we install Flume agents on those Windows servers? Yes. Okay. Because I think it runs, because it is written in Java. So it should be able to pull the data. Okay, and it basically is using the very minimalistic HDFS communication, which is via the driver, and the driver actually works on all the machines. Okay, all right, all right. Now we talked about many things, or let's talk about Uzi after Mahat. Then it will make more sense. All right, we'll talk about Uzi after Mahat. All right. So what exactly is Mahat? Although Mahat is being rewritten and it's being continuously changing, and they are also moving Mahat to Spark, but we'll just go through a very basic use case of Mahat so that you get the understanding about what exactly is Mahat and also get a great use case in place. All right, so Mahat is a scalable machine learning library which is built on top of Hadoop, and it's written in Java. It was driven basically by a paper on MapReduce for machine learning on multicore by NGETL, NG and Company. And it is started as a simple Lucene subproject but became Apache's top level project in April 2010. And who is Mahat? Mahat is a keeper of or driver of elephants. Okay, in a literal sense. So basically, to do a lot of machine learning on the cloud, Mahat is the solution. Okay, all right. So before we go into Mahat, let's talk about machine learning. Machine learning is essentially programming computers to do certain tasks or optimize performance using example data or past experience. The way humans do the work, in the same way, machine learning also does the things by inferring and taking the taking the steps. Okay, it's a branch of artificial intelligence. Its objective is to design and develop algorithms. So machine learning combined with robotics and few more things become the AI. Okay, so machine learning does not deal with the robotics, it only deals mainly with design and development of algorithms automatically. Okay, so plotting a graph in the most simple sense, plotting a graph and then extrapolating the data is the basic form of machine learning, where we are providing the input data and then it's trying to inferring the future, it's trying to predict the future values of y based on x. Okay, now that is the most simple form of learning and trying to predict things. And basically, the computers evolve behavior based on empirical data. The most easiest example of machine learning again is taking a lot of values for x and y, create a graph out of this, and then trying to predict the value of y based on x. But this mechanism of doing x and y is good only in the case of continuous values. Okay, if you remember, there used to be a method in which we can create a graph using x and y values. Okay, and then we have this equation in linear algebra, we call it in linear algebra, where we had lots of x and y values, we try to fit in a curve and then try to predict the future values. Okay, so that also is the most simple example of machine learning. All right, now there are three kinds of machine learning, or let me take a break and then we come back and discuss in detail. What do you say? Yes. Is it cognitive learning like IBM has Watson? Yes. So Watson is really, really great machine learning tool. All right. So let's start after the break. So we'll say break for 10 minutes. Back by 10:13 p.m. IST. Hi everyone, I'm back. Should we start? Hi, should we start now? Alright, alright, alright. To give you a good example of what you call a machine learning, let me give you a good example. Okay, machine learning Mario. Alright, yeah, here it is. Alright, so I'll try to explain what exactly is going to happen in this. Alright, so in this video, what he did was he built a game emulator for the classic Mario. Okay, so here, what exactly is happening is, so in the typical scenario, we play the game in Mario by pressing arrow keys, and then we win. So, how many of you have actually played this game? Has anyone played Mario? Anandita has played. Okay. Anandita has played. Lloyd has played. Sanjay has played. Okay. Okay. All right. All right. Okay. All right. So, Lux is saying, I watched my son playing forever and most of my childhood. I think it is. Okay. So in this, what he did was, nowadays you can play this game on emulator. If you don't have a proper NES control, what you can do is you can download an emulator, get the cassette ripped, and then, like in virtual machine, you can play it. So here, what he did was he let the computer play this game. His algorithm is what is playing this game. Initially, it's he who is playing. Now, after some time, it's so initially this is how the computer is playing the game. You see that? It's so stupid. So it's like very naive. It's just jumping randomly again, and now this time the computer is learning continuously. Computer is initially it was pressing random keys and observing if his score is increasing or not. Okay, so computer was told that you can press any key you want, all you will get to see is the screen score. Okay, that's all you will get to see, the score. Now computer is automatically learning to play this game by playing it randomly. Now you see it is somehow able to play the game. After a couple of weeks, still after a couple of days, this is the situation again. It died jumping there. Now this time, after few more tries, it has learned that if it kicks the coin or if it jumps on them, it will get the numbers. So it's learning. Nobody taught the algorithm to do anything. It's the algorithm which automatically figure out how how to play a game. Now at this point, it also jumped again and is able to play really well. See that? Is able to play really well. Okay. So if you have not watched this earlier, I'm just pasting the. Now what you will be amazed is, so he made some fixes to the algorithm. That's what he's going to explain. Now there were a situation where Mario was getting stuck in this corner forever. So he made some modification into the machine learning algorithms, and now he's able to do this. Now look at the magic. After a few weeks of playing, now Mario is like perfect. He's playing perfect game. You see, you can see the game. It's playing just perfect. See, all right. So nobody programmed it to play. It automatically learned. Now you will see few of the magics as we go forward. Okay, now it's playing just okay. It purposefully died because it'll get another chance and then it'll play. So although it looked randomly that it has died for no reason, but it has purposefully uh, computed that. Now see the magic, few of the magic. See what did he do? He figured out. The computer figured out a bug in Mario. So the moment the Goomba was coming from top, it started moving down, and that's how it tricked the program into winning. Okay. All right. Now Sanjay's question is, how can algorithm learn at its own? So what he did was he let the algorithm keep on pressing random keys and observe the response of Mario to it. So program is learning from the game. Program is learning from the data point in game. The way when we play the game, nobody teaches us the rules. Nobody teaches how to play the game. We figure it out by ourselves by pressing random keys, and that's how he also did that. Now you can see. Do you see a great? Uh, I mean, a way to build the algorithm? Even if I had sat down and written this algorithm, or some genius people have tried to build this kind of intelligent bot which will play Mario, okay, they would never have figured out the bugs which this AI algorithm figured it out. The machine learning algorithm found out the bugs in the game which I played for most of my childhood. Okay, so reason is that it could continuously play without any exhaustion. It could continuously gather more and more data and take a decision on that data continuously, and that's how it learned to to play the game really really well. Okay, so and then he did not have to program it to play other games. He was able to play other games also. Okay, so he was able to play other games very well. You can see that. Okay, so basically after practicing a bit, computer was able to play any game, and that's the holy grail of machine learning. Okay, did it make sense to you? Sanjay, was I able to answer your question? So it pressed random keys and observed the behavior of these keys by observing the memory of the game. Not the screen, but the memory. Alright? So when we say learning, learning means taking in account the data points and then predicting the future. For example, how did we, when we build algorithms to predict the value of something, what we do? We we take the value of x and y, plot it on the graph, and then we start extrapolating. That is prediction. And that prediction, if these x and y are, instead of two variables, if there are 200 variables, if you had to do the same thing, then you need sophisticated algorithms. Okay? So it's basically learning based on empirical data, and that's all. Correct. So this is Vidya's point. So it saves what key was pressed and what happens and refer to it. That's exactly what it does. Okay? Thank you. All right. And that's how the whole game is built. All right. So a common thread about in machine learning, which before you think that you can apply machine learning everywhere, the important part you should understand is that machine learning is great only if you have great amount of data. If you have like hundreds of records and you think that suddenly using machine learning you can do the predictions, it won't be any useful. Okay, it won't be any useful, and that's why big data and machine learning go hand in hand. Machine learning works on big data, while big data tools give the ability to handle storage and churn humongous amount of data. Now there are generally two big categories of machine learning. One is supervised, where using the labeled training data to create classifier that can predict output for unseen inputs. Supervised learning is like hand holding. Okay, it's like if this happens then this would happen. So we are training somebody, a training algorithm saying for this input this is the output, and for that input that is for that input that is the output. So we keep on building this data, so we have a clear understanding of what is input, what is output, and we tell the question to computer would be, after we have trained the computer, the question would be, here is the data, input data, and give me the output based on the previous data sets. And that's all is about supervised learning. Now there's another form of problems where you have got humongous data and we say find similarities in these 10 records, or find similarities in these 50 records, or you might ask computer that these are the emails, please classify these emails automatically into three groups, okay, or six groups. You okay, so you can say that marking something spam or non-spam is supervised learning, because Google guys must have gathered lot of data on spam, and then did a basically a supervised learning on that. Okay, so they gathered a lot of data on spam, trained the computer to do the spam identification based on the past records, and it automatically started giving the which one is spam, which one is not. They did not have to code it. Okay, just based on huge amount of data they had gathered, they could build a great algorithm for spam filtering. Now unsupervised learning is, given all my emails, can you create 20 buckets and automatically put my emails in those 20 buckets? That is unsupervised learning. Okay, or given the whole human species, create a chart, create a great graph, okay, of the generations, like or given all the species of the globe and their characteristics, like what do they eat, how much they weigh, how big are they, and what is their lifespan, what is the color, what kind of digestive system they have. If we are given all of this information about all of the species, these unsupervised learning algorithms will automatically classify these into hierarchical systems, as in hierarchical structures, that humans came from monkeys, monkeys came from somewhere, so they will automatically classify, or you can say in another word that monkeys and humans are most closest to each other, so they will put it into under a single node. So those are the examples of unsupervised learning. The third one is semi supervised learning, as in once we have some amount of information about the keywords, okay, in the past, and rest is known to us. Like for example, we know that the this file belongs has some keyword in the name, but we don't really exactly know what does it have. So somewhere between supervised and unsupervised learning is semi supervised learning. We have vague amount of information, not very detailed amount of information about each data points. Okay. All right. Here is a question from Sanjay. So, if a gamer always fails, the machine will always fail too. Yes. So there are chances that so there could be two cases. One is the way the game is designed, nobody is allowed to succeed at that point. Okay, but there could be a scenario where gamer has not solved the game properly, okay, and that's why gamer is failing. That kind of things could be overcome, like we just showed you the things which normal gamer could not do and the program did. So this AI figured out that if Goomba is jumping on you, start moving downwards, and that way you will get the coin. So in a collision, it's very difficult to predict who hit who. Okay, and this program figured that out, and figured out that if Goomba is jumping from top and you move downwards, then you get the point. Okay, because that means that you are also moving down, as if you have jumped on Goomba, even though Goomba has jumped on you. All right. So, and also please note that if these programs, the way these programs are built, there is a randomization on both ends. There's a randomization in the game and there's a randomization in the program as well, that it tries to press some random keys sometimes. Now because of this randomization, the results will be different. If you train your program, the results might be different than mine. Maybe your program may never find this bug because of the random factors. Maybe it did not happen in the lifespan of your Mario. It might happen in case of my Mario. All right. So there could be these situations as well. Exactly the scenarios which humans also face. All right. Lux is saying that if anybody is interested in machine learning, there is a free course on Coursera. Yes, that's correct. So yeah, it's a good course by Angie. Andrew Angie, it's a good course if you want. All right, but I'll be very practical oriented, not theory oriented in this. All right, so you can do a lots of things with machine learning. So anything which humans found it difficult to do, machine learning comes for a rescue provided you have enough data. So including image detection, DNA, and whatnot, speech recognition, handwriting recognition, and everything could is being solved using machine learning. Now, the important thing which we need to understand, although machine learning is completely a different branch and it's a huge thing to learn, the things which I want to emphasize on is when the data grows big, your tool becomes different. So if you have few lines of data, you can do the analysis and charting using your whiteboard and the marker. Okay, if you have few lines of data, say 20 lines of data, okay, and you can easily visualize it as well as do the analysis of these few lines using your whiteboard. You don't need a computer for this. But as the data grows bigger into kilobytes or lower megabytes, then you would require sophisticated tools, okay, such as MATLAB, Octave, and R for processing and visualization. Okay, for analysis and visualization, the tools will be same. R can do both. But when your data starts growing into lower GBs, as in 1 gigabyte, 2 gigabyte, when the data doesn't fit into the RAM, then your tools change. Okay, so at that scenario, when you have lower a few gigabytes of data, if few gigabytes of data, your analysis and visualization tool will be different. For analysis, you will use NumPy, SciPy, Weka, and BLAS and LaPex. And for visualization, you will use tools like Flare, MCharts, Raphel, and Protovis. But when your data goes into gigabytes or terabytes, okay, beyond few gigabyte, it goes to say 50 gigabyte or 500 gigabyte or terabyte or petabyte, then first, there is no visualization tool for such kind of data. Reason being, it doesn't make sense to visualize this kind of data. The best way to do, if you are really forced to visualize such data, you should sample it and visualize. Reason being, if you have petabytes of data, human eye cannot see that many points. Also, you don't have those many points on your screen to display the data. Okay, therefore it doesn't make sense to try to visualize that amount of data. You can just simple compute the sample and use the lower GBs of visualization. Okay, but for analysis, we cannot say this. Analysis could be done, and machine learning could be done on this kind of data. And only then, if we are able to do machine learning on this gigabyte data, only then we will be able to astonish our customers, our end user with these brilliant results. And for analysis, we use Mahout, Graph, and GraphX, SparkR, and MLlib. SparkR, MLlib, and GraphX are all part of Spark, while Mahout and Giraffe were basically the older tools and are used for analysis. All right. Now we will just quickly go into a recommendation engine, and you all have to help me in this. Okay. So let's try to see what does Mahout do. So Mahout is a recommendation engine, and whatever so so we are going to generate the recommendations based on the movie ratings. Given the history of which people like which movie, we are going to generate we are going to generate the recommendations. All right. So for that, we basically need to prepare our input in three column format. We'll have movie ID, user ID, movie ID, and rating. User ID, movie ID will be numbers, while rating will be a decimal. Okay, user ID and movie ID will be the numbers, as in long, and rating will be the decimal. And we will call Mahat. We'll feed this data to Mahat, and Mahat will give us who will like which movie and how much. By clustering these users based on their movie preferences and then suggesting the movie to each other. And there are multiple algorithms, but we will just we'll just think about this. So let's try to do quickly. Let's try to, okay. All right, let's try to. So what we'll do is you also can download this open source data on movies, and you can download from group lens. And I think we already have this data in our HDFS. If it is not there, we will make it there. Okay, so do we have this data? All right, it's not there. Yeah, this is there. Okay, so this is the data we have already uploaded into HDFS in slash data slash ML 1 million. You can download it by yourself if you want. You can simply say wget and this file. Okay, it is basically 1 million ratings of movies from the users. Now you can unzip it, and then out of this data, if you take a look at where is the ratings dot dat, so we have this data which is colon separated. We want to convert it into comma separated because that's what Mahat wants. And how will we convert? And we don't want the fourth column. Fourth column is the date on which the rating was given. How can we remove the fourth column and we have comma instead of double colon? Anybody quickly? So you have got a huge file, and what we want to do is we want to convert this into comma separated and remove the last column. We don't want the fourth column. Anybody? Lloyd says use SCD to replace. Anybody else? Good. Lux says, Kanaka says yes, SCD. Lux says use Hadoop streaming and pass regex. Good, good. Anybody else? All right, use regex, that is Sanjay. So which tool should I use? Because I don't agree with SED, because SED will try to bring this file locally first, and then we'll apply SED, and then we'll try to do all that. Okay. Even awk will be having the memory issues. Okay, can we use pig for this? Good. Thank you, Lloyd. Me and you same time. Good. Good. All right. So yes, let's try to use pig in this case. I have put down both ways. One is using the local commands. You can use the local commands like cat ml this and then this. Okay. Also, if you could use, you could actually use a streaming job with this as your mapper. With this as your mapper, you could do a streaming job. Okay. I mean, only this up to here. That's it. If you put this in a mapper.sh and then pass it to, or in the mapper command, you just give this as the mapper command and row reducer, then you will get the results anyway. So I will try to use the pig for this. All right, we will say slash dat slash ml 100 ml1m. Okay, that is the folder, right? So we have ml1m. Good. And then this. All right, let's try to launch pig. Okay, so what we are going to do is, all right, next is, so what we did was we iterated through all the records and generated the picked only these three, and afterwards we are storing it as comma separated data. All right. Now there is a point from Lloyd that shouldn't it be double colon? Actually, this pig storage only take single comma. single character. That's why we have used single character, but that doesn't make much of a difference because we are picking up 0th, second, and fourth, not first, second, fourth. Because if you split it by colon, what would happen is first record will be 1, second record will be empty, third record will be 1193, then fourth record will be empty, fifth record will be 5, and sixth record will be this empty, and seventh record will be timestamp. And that's what we have exploited here. Yeah, makes sense, Lloyd? Okay. So yes, now let's check. Has it created? Let's go to our home folder and check if it has created. What was that? Ratings dot csv. What was ratings dot csv? Yeah, it is there. It has created this folder with 11 MB of data. All right. So these are the ratings of users. All right. And also note, it's not Mahat. This particular algorithm is called user to product recommendation. We are giving product recommendation to the users. All right. So any product, instead of movie, you could put any products. Okay. And the result will be the recommendation. Now, this is the folder which contains our data. Now, what we can do is we can feed this to our Mahat. And how can we feed this to our Mahat? Let me change it a bit. Yeah, we have already changed it. Okay, we have already copied it. And also now let's just try to exit pig and delete. All right, there is no such folder. Now for launching Mahat, you have to specify where is your Java home and then run your Mahat. Okay, so I will try to run it. All right, here we go. So what we are doing here is we are saying Mahat generate recommendation by saying recommend item based minus s similarity log likelihood. This is the algorithm or strategy which we are using. This is our input folder or file, and this is our output folder or file. Okay, sounds good. Let's try to execute it. All right, no problems. All right, so it will take some amount of time to finish. Okay, because the generation of recommendation is a complex process. It takes fair amount of time, and that's why it is, if you remember the three V's, generation of recommendation is considered as the last V, which is variety, which is complexity of a problem. All right, which is complexity of a problem. And so it will take some time, and once it is done you will see the data in this format. It shows that for this user 6029, this particular movie is a suggestion, this is one suggestion, this is one suggestion. So in case you are interested in finding your movie ratings, so what you can do is, I'm being very so here. So what you can do here is you go into this data folder. All right. Where is the data folder? Here. Okay. Look at all the movies and give these movies the rating. Okay. You give the ratings your rating, and add yourself as another user. Okay, and so you add yourself in ratings, add yourself in another user, and then once you have generated these results, join back the data to get the movie names. That way, you will get a great movie recommendation for yourself. Did I make sense? I think I would try that this weekend, maybe on Monday, Tuesday. I'll try to actually get the movie list out of this. All right. So I'll put myself in the users, okay, and I'll rate all the movies which I've watched so far, and then generate the recommendation, and then join my recommendation with the movie name, and that way I'll know exactly what movie should I watch. Sounds good? You should also try the same thing. All right. That way, you yourself can also build a great tool which can generate movie recommendation for anybody who is visiting your website. If your user is starting to give the ratings to various things, and then on the basis of that, you are generating recommendation. Okay, and you are storing this information by this user for the future customers to your website also, and that way you will be able to use it. All right, so it's doing something is it'll go into multiple passes and it'll take considerable amount of time. All right, so now you can see that the data is only 10 MB. Okay, and still it is going to take around 10-15 minutes not 10-15, at least 5 minutes of time on 3 nodes. Okay, so it's actually humongous time for just 10 MB data. So it's neither volume nor velocity, it's just the variety. It's the variety of problem which we are trying to solve. Alright, so that was Mahat. There are other algorithms which are part of Mahat, which such as similarity log likelihood, similarity co-occurrence, and Tanimoto coefficient, and city block cosine. So these are various algorithms that generate recommendations, and you can use any of these. Okay. Log likelihood and Tanimoto coefficients are the easiest one, and generally people are moving to Pearson correlation. Okay, people are moving to Pearson correlation. All right, so there are many other things that Mahat can solve. As we talked about three things, one was supervised learning, other was unsupervised learning. So the easiest thing which Mahat actually started with is collaborative filtering, meaning giving recommendations. Collaborative filtering is another word for recommendations. Second is clustering. Clustering is basically the unsupervised learning, while collaborative filtering is supervised learning. Okay, clustering is take the items in a particular class and organize them into naturally occurring groups such that items belonging to the same group are similar to each other. So automatic classification can be a great use case for Maha. Then classification, as in learn from existing categories, then assign unclassified items to it. So clustering and classifications will be very similar to each other. Okay, so under clustering classification, there are many kinds of classification. One is just n items, and other is creating the hierarchical classification. The last one is the frequent item set mining. It analyzes items in a group, example, items in a shopping cart or terms in a query session, and then it indicates which items should typically appear together. All right. So these are the various use cases available right away in Mahat. So Mahat is a great library of algorithms, but it has been rewritten and it has been there has been little better ones available as of today, but still Mahat solves a large class of problems and it makes it accessible to all the end users. The great algorithms are part of Mahat. All right. So this was Mahat. Let's just go with our Uzi as well. All right. So let's try to see. Okay, it's still running. All right. So that was Mahat. All right. So let me take a quick case study. All right. So I'll just take a case study of my recommendation engine again. So as part of recommendation engine, what we were doing is we were gathering Apache logs. So I'll tell you what exactly we are talking about. So at ad agents, advertising company, so in Mobi, I was working earlier. So what was I doing is I was all right. So let me take a further step back. So there's a company called InMobi, which is similar to like Google Ads. And what do they do is they display ads inside your apps. Okay. When you start playing a game, there will be ads that will be displayed on your screen, right? On the screen or at the below. So those ads are generally coming from InMobi. So at InMobi, my objective was to to display the display the recommendation for the user instead of displaying the it, display the mm, display the recommendation that you may also like these apps because you are playing this app, this game, or you are using this game. So based on many parameters we were giving very great recommendations. That was my objective. That's what I was working at for around 2 months, 2.5 months. So we launched it and it was very successful. So the idea was that we know the user. Every time user asks us for an ad, we know what game he is playing right now and what kind of what time is it, what is the geography, and how many times this user has asked the same game again and again. So we note it down as part of our Apache logs and it get automatically recorded every time, because every time user is being served an ad, a request is coming to our Apache server that serves the ad. So we were given this all of this log, and this log was around 200 terabytes of 6 months. Okay, 6 months log of which ad was shown to who and what was that person doing at the time, what app they were using. So with all that information, we know the geography and everything. So our objective was to build a great recommendation engine. All right. Now, is the problem statement clear to everybody? So what exactly we did was, after we gathered the logs, so first was to gather all the logs, then clean the log and prepare IP address, I mean user ID, application ID, and what was the next thing? Yeah, that's pretty much we did. Okay. Now after cleaning the log into user ID and app ID, we need to convert it into how much this user ID likes this app. Okay. So, and how would we know this rating? We can actually predict this rating by counting how many times this user has played this game. Okay, so we basically did a group by on the data and did the rating. All right, so based on that, we prepared the rating, and rating was, so we did group by and then normalize the data. Okay, normalize the data, and that way we were able to cleanly prepare this three column system. Then we passed it to Mahoth, and Mahoth gave us the Mahoth gave us user ID and app ID 1. These are the recommended app IDs. This is the recommended app ID 1, and the rating was something like out of 5, and so on. Okay, so recommended app ID 2, and so on. So we converted, so Mahat converted this into this. Once it was done, we took this data, we took this data, we moved it to our Apache server, which was serving the results, and then we started displaying it as ad. Instead of ad, we started displaying that you may also like these apps, and that is how the whole recommendation system was built. Sounds good? Now, why am I talking about this? I'm talking about this is because it involves multiple phases. It involves multiple steps. We had to clean the data, churn the data, normalize the data, and then run Mahout. The process was far more complex than what it is being displayed here, because Mahout takes the user ID as long. So, and our user ID were big string. So we had to convert these user ID from string to long by keeping the mappings, and those mappings had to be reverted after the results have been generated by Mahout. So those kind of churnings also we had to do. So, as a part of our single project, there were many, many things which we were doing. And at that time, we were using something called Azkaban. We were using Azkaban as scheduler, and Azkaban as scheduler to generate, to execute our workflow, because we were using multiple tools to do multiple things parallelly at multiple times. And therefore, we needed a scheduler. At later point of time, we removed it and moved to Uzi. So this is exactly why Uzi is used to execute many things in an organization. So first we did Hadoop streaming, and then we executed some pig script, and then we executed our Java code, and then finally we executed Mahat. So there were multiple parts of our problem, and such kind of problems are best solved using Uzi. Okay, was I able to give you a clarity on what exactly it is? All right. So Uzi is a workflow scheduler system to manage Apache Hadoop jobs. And workflow jobs are directed acyclic graphs of actions. Okay. I hope you are clear about what is directed acyclic graph. Coordinator jobs are, so other than providing you a workflow, it provides you a scheduler as well, as in there is something called coordinator jobs which can be triggered at a time or data availability. It is integrated with the rest of the Hadoop stack. All right, it is integrated with the rest of the Hadoop stack and is scalable, reliable, and extensible system. All right, so A DAG is something like this. It's a directed acyclic graph, as in it has no cycles and there is always a direction from one node to another. For example, 5 depends on 11th task, 11th task depends on second task, and 11th task also depend on ninth and 10th, and 3 also depends on 10, 3 depends on 8, 8 depends on 9, and so on. So to get 5 executed, or if we ask, what are the things you should be executing first and second and third and fourth and so on? So the answer would be, please execute 10th, okay, and then execute ninth. Ninth or 10th can be executed together, and execute after ninth and 10th, you can execute 8th, and then after executing 8th you can execute 3rd and 7th. No, you can't execute 7th. Then you can execute 11. You can execute 2 and 11. Okay, so you can see 2, 9 and 10, because they are not depending on anyone, they can be executed initially, and after that, once those have been executed, you can execute 11, 3, sorry, yeah, 11, 8, and 11 and 8 is what you can execute after 9, 10, and 2. And once you have done that, you can execute 5, 7, and 3. So this is the execution plan. If we are given a kind of a dependency, who depends on who, we can predict which one should be done first and last. All right. And that's what is a directed acyclic graph. All right. So I'll try to show you how does it look like, and how to execute an OZ job. Okay. All right. So Oozy workflow looks like this. It looks really, really ugly, but let me try to make it a little better. So an Oozy workflow, when we define the jobs, the in interdependent jobs, we generally define it in this manner. We say that start and end, what to do when it ends successfully, and what to do when it gives an error, and what exactly does it do inside. So this is the XML. So this is the full project's XML. That in this project, this is the starting point we call word count. And what does it mean by word count? There will be an action with the same name called whatever you define here. So as soon as this workflow run, it will look for start node, and then this will take you to this one. And from there, inside an action, map reduce is happening. In case this map reduce is successful, it'll go to OK, otherwise it'll go to error. And inside map reduce, we are telling where is our job tracker. These variables are coming from property files. I'll show you those property files. And this is our name node. And these are the arguments. These are mapper class, this is the reducer class, and this is the input directory, and this is the output directory. So this is the way you can define your map reduce job. Similarly, action could contain multiple things. It could contain pig script, hive script, and whatnot. So this way you can define your workflow, and once workflow is done, you can execute it using Oozy. And in Oozy, sometimes you have to have parallel workflows. Okay, download data from Hive and download data from, say, HBase. So those kind of parallel workflows could be there, which are independent in nature. So you start at some point, you fork it, and then you start executing second and third, and then you join them, and after joining, you can execute something else, and there'll be a result. And the XML of the same thing looks like this. All right, I'll try to do that. Oh, okay. So first job got started. It has some map reduce in it. Then there is a fork. So we are saying that once this action is successful, then send it to fork. So inside fork, it will execute second job and third job. Inside second job, there is mapper. There is some work going inside. There is third job in which there is something going on, and finally, both of these, second and third, they are saying okay to join. As in, once they are successful, go to join. And inside join, we have this particular action. This action will be executed only if both the jobs have finished. And then for action, we have OK to end and error to something. So this way, we can create our workflow and get it executed on Uzi. Let's try to execute one running example. All right, let's go to Hadoop 2. I think it's already done. So do we have Uzi examples in our data folder? Yeah. So these are the examples which I have uploaded for you. And in this is our main project. This is our project XML. Inside this, there is a folder called input data. All right. In this input data, there is some sample data. All right. And inside source, so the general strategy is to put your all Java code here in src. Okay, and this form will define how to compile your Java code. And under apps, you have various code related to apps. Okay, if you have, you can put your Hive script here, and every the workflow required for Hive could be here. Okay, and the workflow will be here. So under apps, you put all your Uzi workflow, and you inside src you could create your Java code. And after compiling Java code from src, it will put the output inside apps, and this is your input data. All right, now let's have a look at various workflows. Let's go for, say we want to see MapReduce. Where is MapReduce? Here. So the workflow of MapReduce looks like this. You can see that there's a queue name, there's mapper class, there is all of this information. All right. So we have, all right. So we can copy some of, we only need one file from there. We only need job.properties. Okay. So job.properties we can copy from examples. Okay. And copy it locally. So we are on which host? Hadoop one. Okay. Hadoop copy Hadoop fs minus cp, or we can say copy to local, and this is the folder from which we are trying to copy data slash Uzi slash examples. All right. So this job.properties contains the information about our system. It says that our name node is this, job tracker is this, queue name is default, example root is this. We can put the name of the folder, which is slash data slash Uzi. Uzi, is it correct? All right. And then examples. Okay. And then our Uzi workflow path is inside MapReduce. Okay, output directory is in our home folder, MapReduce. All right. Now, once we have defined that, what we have to do is we have to call Uzi and run. We have to call Uzi. We have to say Uzi job is this, and then config location. Config location right now is is in is in job properties. It says the app directory does not exist. What mistake did we make? Does it want the app directory to be local? Alright, no. Actually, what we have to do is here we have to remove all of this. Okay, we have to delete this. Okay, we have to, yeah, this is good. So it has executed the job, and let's see what happens. So if you want to see what's going on with this job, we can quickly see. So it's saying that it is executing it. All right. So let me, one thing I've missed. So we are saying, Uzi, this is our job which we need to be run, and this is the host on which we are running the Uzi server, and the config properties are in this job.properties. So only thing we have local on this machine is this job.properties. That's all. Okay, that's the only thing we have on this machine. Rest of it is in HDFS. All right. So this will execute the job, and we can have a look at all the jobs available at. So we can also take a look here, and there were some job UI, right? Where Hadoop 18088. Okay, so you can go to 8088 and see what jobs are running right now. Okay, so it shows that there is no job running right now. So this is okay, this is somebody else's job. Did it run? So pig script we ran, and okay, not application type. All right, I think it must be running. There's nothing wrong in it. All right, job. So this is the job which is supposed to be running, and it's still running actually. All right, all right. Sounds good. I'm trying to check if it has created the data. Yeah, it does seem to create some data. All right, let it go, and yeah. Yeah. In the meantime, you can have a look at our recommendations. So this is the recommendations generated by by Mahat. Okay. You can see that for user number one, these are the recommendations. All right. Sounds good to you? So that was okay. But I think these jobs are running here. This is the one. All right. Let it go. Let go. So, so one way was to use this command line way, and because mostly in production environment, this is how you will be doing things. You will create your project in the format which I have showed you just now, okay, and you will be running the project. You'll compile your project maybe through Ant, or maybe through Maven, or maybe through some other tool, and then you will run your workflow in the same manner the way we tried to run just now. And further you will be using the Uzi scheduler as well to schedule the jobs. Okay, you can create a coordinator and then you can schedule the jobs. Okay, also it provides you a very good and beautiful interface for execution. Say for example we want to say 29th August, and all right, so instead of typing all of that XML, we could also create our MapReduce job by dragging and dropping here. So we could say this is our MR job and this is some other job, and then we could pick up the jar from somewhere. So let's say I'm just giving some arbitrary jar file. And before execution of this, do we want to delete a folder or create a directory? Okay, before before this being executed, and sometimes you want to extract out the properties into somewhere, or you can keep on putting all the properties like what is your mapper, what is your reducer, and so on. Okay, you can do that by defining it here. Similarly, let's say parallel to map reduce, you have another job called pig. If you drag and drop on the same block as other one, you will create a parallel workflow. This is our pig. Okay, this is our pig script, and we are saying our script name is, let's say, has anybody created a script name? All right. So, okay, hive jars. let's just give some random script. Okay, so now you can see that when I dragged and dropped pig in on MR, it has created it as parallel workflow. There's a fork happening here, and at the end of it. So if you want to execute something before the fork is happening, you can drag and drop, say, Hive. Okay, here this is my Hive script, and the Hive script. Let me just pick and choose any of the scripts. Say, okay, although it's not a script, just for the sake of it, giving example. So this way you can have, so start, then run Hive. After the Hive, execute MR, execute pig, and before everything, let's say we want to say something like very generic, or something like a Java program. So you can do that by picking from here and dropping it here. All right. So instead of writing all of that in XML, you can write from here also. Also, once you have done you and you have saved it, you can also copy the XML of this one. Okay, I'll show you. All right. So there was one edit workflow, upload, source history, submit, schedule, copy, and there was one way of seeing the XML. There's a way to see the whole XML of the process as well here. All right, never mind. Okay, so other than this, you can create a coordinator which can basically schedule what needs to be done when. All right, that's pretty much about Uzi. Okay, so these all things could be done from the UI, and there is a action for almost everything in Hadoop. Okay, you can create a generic action. You can call some other workflow from within one workflow using sub workflow. You can use disk cp command of Hadoop, and you can ssh and you can execute any shell script. You can also execute MapReduce streaming, and you can execute scoop commands. All right, so almost everything, the whole of Hadoop is covered in Uzi. There are corresponding action for every command inside Hadoop. Okay, so all right, so that was about Uzi. All right, so here are few of the assignments for you. Im- Okay, one is import data from MySQL to Hive and back. Build an Uzi job for fourth problem of session 2, which is voting problem, the one which we did earlier, because it has two stages. And third is that prepare the movie recommendation using the data from movie recommendation for yourselves, using the data of group lens and Mahat. Okay, using Mahat using Mahat with the data of group lens and your preferences. So these are the three things you need to do as part of today's assignment. All right, any questions at this point? All right. So tomorrow we will mainly cover Spark. The rest of the things are very small. Okay? All right. So, any questions at this point? Anandita, Jairam, Joshi, Kanaga, Lux, Lloyd, Ravikant, Richard, Sarvna, and Vidya. All right then. See you tomorrow. Have a great day. Bye bye.